Hi, welcome to the universe of first-order RC circuits. In this video, we will give you a practical and interesting example. The total response of a first-order RC circuit where there is a voltage source and a switch in series with a resistor and a capacitor. The switch, K, is initially open, ensuring that the capacitor current, IC, is zero and its voltage, UC, remains constant. The capacitor is charged with a voltage U0 at time 0. At that instant, the switch K is closed and remains closed from that moment on. We want to know how the voltage and the current behave from that instant onwards, that is, for t equal or greater than 0. In here, you'll find math formulas, some illustrations, and graphs, so you can pause the video whenever you need a little bit more time to let the information sink in. But let's get into it. In a circuit with such initial conditions, we have a voltage U equals E for t equal or greater than 0. The equation of the circuit is as follows. In case you want to remember how to get here, you can watch our introduction video to first-order RC circuits. Alright, knowing the value of U, which is E, we can replace it in this equation. Then, to determine the voltage across the capacitor for t equal or greater than 0, we need to solve this first-order ordinary differential equation. First order because it only has the first derivative of one dependent variable, UC, with respect to an independent variable, t. In this equation, E, R, and C are constants, and UC is the unknown. The solution to this equation is the following expression. We can see that this solution equals the sum of the forced response and the natural response of the first-order RC circuit. Both are explained in other videos in this collection. Be aware that this solution is obtained through the Laplace transform. We can also determine the current through the capacitor, which is exactly the same across the source and the resistor for t equal or greater than 0, which is given by this equation. Once again, we can see that the total response equals the sum of the forced response and the natural response. Well, but how do we get to this equation? Well, it's really easy, through the equations that we went through before. The current through the capacitor and resistor can be determined by the famous Ohm's law that you probably know like the back of your hand. IR equals UR divided by R. In this circuit, the voltage across the resistor is given by UR equals U minus UC, in which, according to the initial conditions already referred, that is, U equals E, the voltage across the resistor equals E minus UC. Knowing that the IR current through the resistor and the IC current through the capacitor are exactly the same current, we have IR equals IC. Ultimately, by replacing UC with the equation we saw above, this one, we get our final expression, which is this one. Cutting things short, these are the equations that translate the total response of a first-order RC circuit, which we can rewrite as follows. But now, let's analyze the graphic representations of these expressions. After a time equaling R times C, the voltage across the capacitor terminals, initially charged with a voltage of U0, reaches 63.2% of the value of E minus U0 plus U0. This time period, R times C, is called time constant, which is represented by the letter tau. After 3 times that time, that is, after 3 times tau, the voltage across the capacitor reaches 95% of E minus U0 plus U0. And after 5 times tau, it reaches 99.3% of E minus U0 plus U0. On the other hand, the IC current through the capacitor behaves in the following way. For the instant t equals tau, the IC current reaches 36.8% of its initial value E minus U0 divided by R. At the instant t equals 3 times tau, IC reaches 4.9% of its initial value, and at the instant t equals 5 times tau, IC reaches 0.7% of its initial value. In conclusion, we can see that the initial value of UC of 0 equals U0, and the initial value of IC of 0 equals E minus U0 divided by R. We can also see that as t tends to infinity, the voltage across the capacitor, UC, approaches its steady state, which is E. And also that as t tends to infinity, the current through the capacitor, IC, approaches its steady state, which is 0, showing that IC only has transient state. But let's take a look at another situation. If the switch K is closed at an instant t equal to t0 instead of at a time 0, we use the same line of thought, with only a few twitches. The voltage on the capacitor will be defined by this expression, and the current through the capacitor by this one. Therefore, the graphs obtained will be the following, where it is shown that the capacitor begins to charge only from the moment t0 instead of at time 0. Thank you so much for staying with us. Keep exploring this universe by watching the other videos we prepared just for you. See you next time and good study session!